Hello, I'm Zhan. Today I will introduce our work, Automated Third-Party Library Detection for Android Applications. Are we there yet? As we all know, Android apps has already dominated the app market for many years. Until now, there are more than 2.7 million apps on Google Play. Without a doubt, the success of Android cannot live out with the numerous third-party libraries because they can help developers to facilitate the whole development process. On the other side, developers also can download numerous third-party libraries from different open-source communities. With the help of the powerful and advanced development tools, they can import different TPLs into their own apps. According to previous research, about 57% of Android apps include AD libraries, and more than 60% of the code in an app belong to third-party libraries. Besides, we also found that there are various TPL detection tools here, and they have different technologies and focus on different research purposes. So that is why we try to conduct this research, because we found even if there are many TPL detection tools, but there are still many mysterious ways are still unknown, and many research questions are unaddressed. For example, consider specific usage scenario. We didn't know which one is the most suitable choice, and we have no idea about which one is the best. How about the detection performance, the detection rate, the accuracy, the efficiency, scalability, and the capability of resilience to code obfuscation, whether these tools are user-friendly or not. Therefore, we conclude our goals as follows. Firstly, we try to build an unbiased and comprehensive dataset to evaluate current publicly available tools. Future researchers also can use our tools to evaluate their work. Besides, we try to get a better understanding of this state-of-the-art third-party library detection tools. And we also try to conclude useful insight to get future work. Finally, we built an extensible framework that integrates all existing third-party library detection tools to provide an online service to users. All above-mentioned dataset and the code of the extendable framework you can download from our website here. This is a link. In order to conduct this research, we need to collect all the related work in TPL detection. Therefore, we defined some keywords and search the digital databases from top conferences and journals, from security, SE, and program language, etc., and try to find all related work in TPL detection. Until we submit this paper, we found 9 related work in TPL detection. Based on the detection method, we divided all of these tools into 2 parts. The first one, we call it machine learning-based method. It also can be subdivided into 2 types: classification-based method and the clustering-based method. The second detection method, we call it similarity comparison-based method. As can be seen from this picture, AD detect is a classification-based method, and LabD use clustering-based method. The remaining tools choose similarity comparison method. Here, we should emphasize that LeapShift implements a module decoupling algorithm to split the non-primary audio into different parts. It cannot identify specific TPLs. Similarly, AD-Detect also uses SVM to distinguish the AD libraries and non-AD libraries from apps. It also cannot identify specific TPS. Based on the collected tours, we found that they have something in common. Therefore, we conclude the TPI detection process into 4 steps. The first step we call pre-processing, which means TPI detection tours use reverse engineering tool to decompare an app and get appropriate intermediate representations. The second step, we call it library instance constructions. TPS tools use 1 or 2 module decoupling algorithm to separate the non-primary audio into different parts. As can be seen from this figure, we can find a decompiled app can consist of 2 parts. The first one is primary module, and the second part is non-primary module. As for the primary module, which consists of the code from the host app, as for the non-primary module, which comes from 1 or more third-party libraries, as can be seen. As we all know, Java usually exploits the package structure to organize the class files. And in general situation, independent third-party library usually have independent package structures. Therefore, some existing tools usually use the package structures to cut the non-primary audio and treat them as a potential TPR candidate. The second step is feature extraction, which means use appropriate code transformation algorithm to extract the code features to present the TPR candidate. Based on the extracted fingerprint, choose the appropriate algorithm to identify specific libraries. Based on the tool comparison, we divide it into 2 parts. The first one, we call it serial-based comparison. We compare it from 4 aspects based on the TPI detection process. We do not elaborate this part. You can refer to our paper. And as for the second part, we call it practice-based comparison. We conducted an empirical study, and we defined 4 criteria to evaluate existing tools. Consider the empirical study. We need to compare these tools, but we just consider the publicly available tools. Besides, we also found library report error in their method, and this tool is still unfixed when we submit this paper. Therefore, we didn't represent the result in our paper, but you can find the detection result of LabD from our website. As for the effectiveness evaluation, we construct a data set which used to evaluate the effectiveness and efficiency. Build the ground truth. We first get the app and the library mapping information from the app brain. Based on the information on app brain, we download the corresponding app from the Google Play with the latest versions. Based on the collected apps, we can ensure the in-app TPS, and we download this TPS from the Maven repository, which includes 59 different TPS with complete version files. Besides, we also use 3 metrics to evaluate current tools. They are precision recall and FE valued. Here is the detection result. Here we can see most tools can achieve the high precision but low recall. You can find most of them just can reach nearly about 50% recall, which means they just can find about half of TPS in an app. LabScout achieves the highest recall, which nearly about 50%. LabReader has the highest precision. Aurelians has the worst precision and recall. LabScout achieved the highest comprehensive performance. Here we give the reason to explain the false negative and the false positive. Here we can see this picture. It's very common in real-world apps. It's a decompiled apps. We can find some strange files. These classes files, they without any package structures. That is, they are obfuscated. This app is obfuscated with the package flattening technology. This obfuscation is very common in real-world apps. But we can say, except Aurelians, existing tools more or less depends on the package structure to build the library instance. Therefore, they cannot handle this kind of situation, leading to false negatives. The second situation is actually the package structure also very complicated. We all know in general situation, independent Java third-party library usually have independent package structures. But when these TPS are imported into Android apps, things will be very different. Here you can see the second case. Library 5, Library 4, Library 6, they are totally independent libraries, but they share the same root packages and sub-packages. Actually, it's hard to cut them out. And as for the second situation, which comes from the TPI dependency, we can see some parallel package structures. Actually, this is also very common. We can find many Java projects also built on other open source projects, etc., and they have parallel package structures. But all of these package structures just consist of a complete Java project. Therefore, if we use the package structure to identify the library instance, it will make a mistake. Here we give an example. You can see it offline. The other reason leading to misidentification comes from the import model. Partially import and the customized import can lead to the code different from the original code of the original libraries, which also can lead to false negatives. The other reason comes from some tools. They only can handle TPS in jar format and ignore the TPS in AAR format, which also can lead to false negatives. The other case comes from Multidex Problem. This is because in Android, the executable Java code is compiled into DEX file that limit the total number of method reference to 64,000 in a single DEX file. But nowadays, more and more apps use a lot of third-party libraries. It is impossible to include all third-party libraries reference in a single DEX file. Since Android version 5.0, it supports to compile an app into multi-DEX file. If it exceeds the limited size, we found the LabReader and Aurelians, they just support a single DEX file and can not handle the multi-DEX problems. Therefore, they will miss a lot of third-party libraries, which will lead to false negatives. As for the efficiency, we also use above-mentioned dataset to evaluate them. We can find the detection rate of different tools have orders of magnitude of differences. Here we can see several tools such as lab ID, lab pickers usually spend 7 hours to find all TPS in an app. But as for the lab radar, it's just spend nearly about 6 seconds. It can find all the TPS in apps. Therefore, lab radar outperforms existing TPS detection tools. Here we can see the reason is because lab radar and the lab scout, they just choose some simple syntax code features to identify third-party libraries, but other tools such as lab ID, lab picker, lab Aurelians, they all include sophisticated semantic information. Extract these features usually time-consuming. And we can see Lab Scout and Aurelians, actually they use the same code features. That is, fuzzy method signature as a code feature, but Aurelians includes method invocation, relationship, and class dependency in the signature. Therefore, the detection time is longer. Here we introduce a method signature, fuzzy method signature. Consider a original method signature is like this, and the fuzzy method signature, which means replace, substitute some field which defined by developers and easily be obfuscated by some techniques, and by replace them into a placeholder X and generate the fuzzy method signature. We also can say it's just use the syntax information. As for the tools, lab picker and lab ID, we can say it takes more times to find in-app TPS. That is because lab ID, lab picker, lab Aurelians, they all choose class dependency as code feature, and extracted these code features is usually time-consuming. Besides, the feature granularity also can affect the performance of detection time. As for the lab radar and the lab scout, they just compare at package level, but lab ID, lab picker, and Aurelians, they compared at class level. The number of classes is far more than the number of packages. The third thing we will compare the capability of resilience to obfuscation. Therefore, we set 2 experiments. The first one were towards different obfuscation tools. Second one were towards different obfuscation strategies. For the first one, you can see this table. Because different tools, they have different obfuscation strategies. Not all tools, they support this called obfuscation technologies. And the capability and the implementation algorithm also different. Therefore, we want to verify the capability of TPR detection tools to different obfuscators. For the second experiment, we aim to investigate how the code obfuscation techniques affect the detection rate of each tool, and which techniques has the most prominent effect on these detection tools. As for this experiment, we set 2 datasets. For the first one, we use a benchmark from the Aurelians. It's released 4 group apps. The first one is original app without any obfuscation, and the left 3 group apps are obfuscated by Pogard, Aleatory, and Dasho. Towards the different obfuscation strategies, we construct this dataset by ourselves. We randomly choose 88 open source apps from the previous experiment, and we use -O to obfuscate them because it has a better obfuscation performance. And we obfuscated these apps by using different strategies, that is, control flow randomization, package flattening, and data code removal. Control flow randomization can change the control flow graph, and data code removal can delete some TPS code which are not invoked by host app. Here is the detection result. We can say the detection rate of all tourists remain unchanged for apps obfuscated by ProGuard. The obfuscation performance of -O is the best. -O dramatically discounts the performance of all tourists. The code obfuscation effect of aleatory lies between ProGuard and -O. That is because different obfuscation tools enable different obfuscation strategies. Even if the same obfuscation strategies, different tools may adopt different algorithms and technologies. For example, for package flattening, program just change the package name, where both aleatory and -O, they can change the package name and the structure. Furthermore, -O also can encrypt the classifiers in this process. Here we can see -O has a great impact on lab radar. The detection rate even dropped by nearly 70%, and the lab ID and the lab pickers show better performance than other tools. That is because we mentioned before, lab radar and the lab scout, they just use simple syntax information without semantic information, but lab ID, lab picker, or aliens, they use class dependency as a code feature. Here we can see some strange. You can find the lab ID's performance is not good. That is because the performance of lab ID is dramatically limited by DEX2J. We found that they usually cannot handle library compatibility problems and anti-decompilation problems. Here we can say the second experiment, we can say lab picker achieves the best performance among existing tools. That is because future granularity also can affect the obfuscation capabilities. And the code feature includes semantic information can achieve better performance. Here we can find, except Aurelians, all tools depends on the package structure. Therefore, the detection rate keeps the same here. For the last experiment, we try to verify which one is the best user-friendly tools. Here we design a survey about all of these publicly available tools from 3 aspects. The first one is setup processing. The second step is usage. The third is the result presentation. We recruit 2 people from different backgrounds to help us conduct this survey. And here we give some apps that they help us to install and run these tools. Here we give some detection result to readers so that they can see which one they like most. And most people usually complain that lab ID is too complicated during the install step. And people usually cannot stand if the tools meet some error or cannot get the result smoothly, they have to wait too long. They usually complain that, and they found lab ID usually have let them wait a lot. As for the result, we can find the lab reader gets the highest score from the participant because it's very simple to use and user-friendly output. And we found the participant gives the lowest stars to the Aurelians. We suggest these tools need to improve the most. Finally, we give our lessons learned. For malware and repackage detection, we suggest choosing lab shift. For vulnerable TPI detections, we suggest users to choose Lab ID and Lab Scout because they can specify the lab revisions. For clustering-based methods such as LabD and LabRadar, actually it's hard to identify the specific libraries because they just generate the package features. As for the component analysis of apps, we recommend LabPicker, which is proved to have the best code obfuscation-resilient capabilities. As for the large-scale TPI detection, we suggest using LabRadar that has high efficiency. For advertising investors or developers who try to choose popular ID libraries in their own app, we suggest they use LabRadar that can efficiently find the common used AD libraries in Android apps at market scale. Finally, we see our conclusions. We released an unbiased dataset which can use to evaluate different TPI detection tools. We are the first to conduct a systematic and comprehensive analysis on state-of-the-art TPI detection tools. We fixed some disadvantages of these publicly available tools and published them again. We released the code of extensible framework and integrate all existing detection tools that can provide an online service to users or provide useful insight to future researchers. Thank you. That is our whole work.